So again, Protoplanetary, and this time we have Planet. So thanks to the facility development of in submillimeter millimeter size of ARMA, so we actually know that lots of this Protoplanetary actually feature this X-symmetry structure like ring and gaps, like what we show here. So what we're looking at is the thermal emissions of this millimeter, submillimeter size pebbles, so-called. So therefore, understand the formation of this ring is basically understand the aerodynamics of this pebble-sized particle inside the protoplanetary disk. So the entire picture is actually very straightforward. So imagine a disk without gas. So the pebble should just follow in the Keplerian velocity. But because the gas actually follow a distribution, so which is denser at the star vicinity, but so less denser further away. So it should have a pressure gradient to support the Keplerian rotation as well. That will lead the gas rotate slower than Keplerian velocity, and therefore will lead a headwind between these pebbles and the gas. So this headwind will basically drag the pebbles and make them lose their angular momentum. Therefore, this should spiral towards the stars. So if we look at the complex equations, we don't need to remember everything, but just note the zero order effect that the pressure gradient itself should be able to trap some dust inside a specific location. So if you do have a pressure maximum or say a gas perturbation at the disk, then you should be able to trap the dust and therefore you form the ring, as we said before. So how to cause such a pressure bump to trapping the dust? So a natural explanation could be that if you put a planet inside the disk, then the planet gravity will push the gas away its vicinity, like the video show here. So therefore, at the outer edge of this protoplanet disk, you can naturally get a pressure maximum, and therefore you can trap the dust inside it. It seems everything is fine, but also thanks to ARMA, actually we also have the ability to track the gas density profile directly in protoplanet disk. So basically in this MAPS large program, what people do is they trace different molecular emissions and try to find if we also can find this ring and gap structure in these line emissions. So good news is yes, we do. But then we want to ask so whether these molecular rings are indeed coincide with the dust ring we said before, as it should be a natural prediction if you are indeed formed by planet. The statistic test of this correlation is actually not so trivial, but so basically if you put all of this line emission on a radial profile, so while the background is continuum profiles and each line here show you a line emissions. So every cube here is a ring peak and every circle here is a gap bottom. So by counting the overlapping fraction, you should get a number directly from the observation. And you should compare it with a non-hypothesized. So say if they are not correlated, so how should this dot really behaviors? So what we do in this work is we try to redistribute these molecular emission lines and rings to make them follow a random distribution. And therefore, it should lead an overlapping fraction like this violin plot. So surprisingly, actually, the real observation is pretty much consistent with a non-hypothesized. So that suggests probably this dust ring and gaps are not really coincide with a gas ring and gaps. So we actually apply this method to all of these 5 disks in the MAPS last program. So overall, there is no correlation, but so we are not going to details to discuss why there is no correlation. So fortunately, we indeed found an outlier. Well, it's actually not so consistent with what we expect. So it is actually a chemical ring coincide with dust gap coincidence. So if we look at the real observation, it looks something like this. So on the leftmost panel, I show the dust continuum of this MWC480 disk. And as you can see here, I marked the brightest annular rings at 100 AU in the solid circle. And so I marked the gap bottoms around the 76 AUs in the dash lines. And I put this circle lines and this dash line also to other molecular maps. And you can find that it's actually not the rings coincide with ring, but the molecular rings are appearing inside the dust continuum gap of this M.480 disk. So it will be very interesting to investigate what's happening here. So, but before moving into planets, we probably need to learn a little bit about astrochemistry. So I'm not an expert on astrochemistry, so we don't need to go through all of this. What we need to know is basically focus on the very simple, very shallow layer. So it's indeed very shallow. So basically, if you indeed expose into the upper layer of the protoplanet disk, you should expose more to the UV flux from the stellar and also from cosmic ray or from whatever source you get. And also because of this UV flux, it can destroy a molecule like CO into atomic carbons and atomic oxygen, which is essential for the formation of the radical molecules, such like the C2H. And if I go back to the previous detection, indeed, the C2H is showing a ring here. So if we summarize, it's like, so the C2H formation basically requires two things. So one is it should have a very strong UV radiation, and another is, so it actually requires the carbon to oxygen ratio is higher than order of unities. Since if it's other way around, you have more oxygen than carbon, so everything should end up being CO rather than the other radicals. Therefore, we try to link this picture with a planet. So say in a cold without planet disk, it's probably basically the gas phase is dominated by CO itself. So there's no other carbon carrier in the gas because apparently, so other carbon carrier has a higher condensation temperature than CO. Then therefore they should be trapped inside the icy pebbles. But the planet accreting can actually heat the planet vicinity as well. So it's not only open a gap around it, but also the planet itself can heat up the disk and also open the gap. So you will also expose the disk more to the UV radiation from the star. So both of these two ingredients are actually very helpful for the C2H formation. And therefore, we want to test this in a more robust way. So we do this in a 2D hydro simulations. So the left panel show here is what we do in the simulation domain setup. So around the planet, we relatively use a higher resolution. So we want to really resolve the flow pattern around the planet. And so a novelty of this code is we actually add a sublimation module into the hydro simulation. That means we can both tracing the icy pebble, and when they are getting close to the accreting planet, which is very hot, they can also sublimate by the planet. Here is a video to show what we do exactly. So at the beginning, the planet is still small, so it's do not change anything. But if we start the simulation, as you can see here, planet will very quickly eating the gas around its vicinity and also sublimating the pebbles, so the ice around its vicinity. So if we go closer to the planet, these pebbles are indeed be sublimated around it and released into the gas. So here in the left is show the icy pebble, and on the right we show how the evaporate pebbles will go to vapors and they can pollute the natural gas. This have a direct implicant because what we are doing here is basically we're assuming that the CO is dominant in gas before, but now we are releasing some carbon carrier ice like methane. This is kind of always true because carbon carrier usually have a lower sublimation temperature than the oxygen carrier, like water. Water have apparently a sublimation temperature around 100 and even 150 Kelvin, which cannot be reached. So if we check the temperature which is reached around the planet vicinity, it's like the planet is accreting its mass in the first panel, so y-axis is time, y-axis the mass, and therefore this accretion rate can be directly reflected to the planet luminosity by converging the gravitational energy into luminosity, and its luminosity should heat up the temperature around the planet. So here we basically study the temperature at the so-called Here radii, so which is the balance between the planet gravity and the stellar gravity. So as you can see here, so without planets, it's only 20 Kelvin at the disk location, but with the planet accreting, it's elevating the temperature to about 40 Kelvin. That's qualitatively different for methane to sublimate. So here I show the same simulation in a different way. So at the beginning, planet is very small, so it do not perturb the disk so much. And also in the gas phase, there is only CO, so the C/O ratio should be around unity. But as the planets go to sublimate the methane from the ice into vapors, as you can see here, so the C/ρ ratio will be elevating locally around the planet. And as we discussed before, so higher carbon to oxygen ratio and more UV radiation penetrate are very beneficial for C2H formation, which can lead a ring-like structure, which is exactly coincide with its gap location. So we actually do a bit more quantitatively study. So what if we change the accretion rate of this planet and what will happens? So in this plot, I show that basically we change the accretion rate of a planet by times a prefactor onto the prescription we use. So as you can see, if you increase the accretion rate, it will also means more violent accretion, therefore higher luminosity as this orange line shows. And this can also heat up the vicinity to a higher temperature. But other way around, so if you lower the accretion rate, so you have a lower luminosity around the planet vicinity. And okay, I'm going to finish. So it's other way around. So makes the temperature do not suffer so much changing around the planet. So if we pick a specific time after different simulation, let's say, so we pick the dash line here. So in the default model, we kind of form a Jupiter mass planet and release a moderate amount of methane to the gas, therefore elevating the saturation. You say that. So in these three simulations with relatively higher accretion rate, we can indeed do this. So no matter it's caused by the higher accretion rate, therefore releasing more carbon to gas phase, or caused by open a wider gap. So with higher accretion rate, you can always kind of match the criteria required for C2H formations. But if you only have very low accretion rate, so you can never really release the methane into the gas phase, and therefore the C2O ratio is overall flat here. So if we indeed see some coincidence between the C2H ring and the continuum gap, it should therefore suggest that we at least have a planet which is currently accreting above this range. So it should rely on in this group rather than this group. Okay, in this slide, I basically show the same figure, but in a different way. So before we say we look at the same time, and now we say we look at the same mass, and exactly it's actually the same story. So only in the higher accretion rate, so you can reach a level of C2H condensate can be detected. And in this low accreting group, you can never really reach the detectable value. So which is rarely detected. Here is the take-home message, and I'm happy to take any further questions, and thanks.